Well, hello physics kids, this is Mr. Galoya coming at you. This is the introductory video for Unit 12, and Unit 12 is Work, Energy, and Power. And, Galileo introduces us to the ideas of time and motion, velocity, displacement, etc. And Newton presents the ideas really of forces. So after Galileo and Newton, after their ideas and after they kind of passed away, people then started using their sort of concepts in some new ways. And that's kind of what the next couple units will really be about. This Unit 12, which is on work, energy, and power, and then Unit 13, which is on a concept called momentum. So before we kind of get into that, let me talk kind of about this middle one first, energy. So in the world and the universe, there's just gobs of types of energy. There's electrical energy, there's heat, fossil fuels, wind energy, solar power, etc. But in a physics class, at least at the high school level, we're really only interested in the types of motion really involved, types of energy really involved with motion. And they're kind of really just three types. And you might really you kind of maybe know some of these from another science class maybe. Oops, let me get back up there to the top. Sorry about that. Let me see if I can get my mouse involved a little easier. Kind of move this over maybe. Sorry about that, kids. Here we go. So you might know again of these types of energy from some of your other science courses, but there's a type of energy called kinetic energy. We call that the energy of motion. And again, there's a way of quantifying this energy. And we symbolize it EK, K, or KE. Kinetic energy is 1/2 the mass of an object times the square of its velocity. That's how we actually get a number for kinetic energy, but it's the energy of motion. So we could maybe take a jogger. The jogger has mass and the jogger has velocity. And maybe the mass is 55 and the velocity is 3.87, and we can just plug everything into this equation and we can get the energy that jogger has. Notice if the jogger is more massive or is moving faster, then the jogger has more energy. Now you might wonder what this little J is. Well, that's a symbol for energy or work. We'll get into that shortly. And basically it's called a joule, and it's given the symbol J. And Joule was a British physicist that lived in the 1800s after Newton and Galileo, and he did a lot of research on energy and work and power, etc. Well, there's another type. We said there were maybe three types of energy that's kind of important, at least in a physics class. The second type is called gravitational potential energy, and this is given the symbol GPE or PE subscript G or U sub G. I typically will use GPE, but it depends on the book and the website, etc. But basically we give objects gravitational potential energy when we lift them up in a gravity field above some sort of a reference line or reference point. We typically use the floor or the ground as our height equals 0 or our reference line. And we can give that object then this type of energy, gravitational potential energy. We can get that by then lifting its mass times gravity, that's that little g, times the height. Let me give you an example here. So if we lift this bottle of water, it's 1 kilo. We lift it 1 meter. On the Earth then, 9.8 is our little g. We would get 1 mgh, or 1 times 9.8 times 1, or 9.8 joules. Notice that on all energy, we're always measuring them in these units called the joule. Well, we also have what's called thermal or dissipative energy. And basically that's kind of due to friction when we're trying to move objects. And friction can cause an object to slow down, and that's dissipative or thermal energy. Often in many of our problems we might ignore this. Pretend we're using what's called a friction-free surface. For example, often a lot of physics books will talk about objects sliding on ice. We talk a little bit about ice because there's very little friction on ice. There's a little bit, but there's very little friction. Now, I gave you equations really to quantify gravitational potential energy and kinetic energy. We don't really have an equation, at least at this level, to kind of numerically calculate this. But it's important really in all things moving that we have to acknowledge that friction can kind of cause a dissipative effect. Well, so the question is, how do objects get energy in the first place? Well, I was telling you that people after Galileo and Newton kind of passed that they were using a lot of their ideas. And people then took the idea of Newton, force, and took an idea from Galileo, displacement, or how far something moves. And they put these together and came up with this concept called work, or physical work, or work in physics. That idea of that word work has a lot of connotations. So, for example, I may go to work one day and I go to school and teach. That's my job. That's work. Well, in physics, work is the product of force and displacement, or how far something is pushed or pulled. When we multiply these two things, we get then this concept called work. Now, we can have work, or we can do work on an object, and we can basically give it, for example, kinetic energy. So if I move this box, or this person moves this box 5 meters with a force of 12 newtons, we can multiply those two things together. We can give that object then kinetic energy. So I do 60 joules worth of energy, 60 joules worth of work on the box, and now I've given it the same amount of kinetic energy. All right, so we're not lifting the box up vertically, we're just sliding or pushing it against the floor. So there's no really change of gravitational potential energy, but there is a change then of kinetic energy. I can put that object in motion, and I can basically take its mass and give it then a velocity. I can do then kinetic energy on the box. Well, we can also then do vertical work on an object. So for example, we can take a barbell and we can lift it up. We're lifting the weight of the barbell, that's a force. We're lifting the weight of the barbell up a certain height. And usually then this height again, we'll usually use y's instead of x's, but it's really a displacement. And again, we often use the floor for our baseline. So we just want to lift then the weight of the barbell up a height. Again, that would be physical work, but it would be vertical work. So maybe the barbell weighs 300 newtons, and he lifts it up 2 meters. So that's 600 joules of work. So the barbell now, the person did 600 joules worth of work. The barbell now has 600 joules of GPE. Okay, I know it looks really complicated. We got these equations. It's really not that bad, kids. We just really have one more concept that we'll discuss. And that idea is called power. All right, power then is the rate that work or energy is done. And when a math teacher talks about a rate, that means we have time in the denominator. So we have work or energy in the numerator and time in the denominator. And so work or energy is in joules, and we put then time in seconds. And so this unit then for power is called the watt. What? The watt. W-A-T-T. It was named after James Watt, and he lived in England, Scotland, and he did a lot of work on power and energy ideas too. So let me kind of give you an example here. Let's go back to the barbell here. So maybe we have two people lifting this barbell. They're lifting the same weight, and let's say they're lifting the same height. And we said that that was 600 joules worth of work or energy. If they take the 300 Newton barbell and they lift it 2 meters. So both, if we have two people doing this, both people exert the same amount of work, and the barbell has the same amount of energy. But one person may lift it faster than the other. Okay, so one person might lift the barbell in 1 second. So that would be 600 watts. That's 600 joules worth of work or energy divided by 1 second. That's 600 watts. The second person maybe lifts it in 2 seconds. So the power would be 600 over 2. Well, that would be 300 watts. So typically then, the faster some work or energy is done, the more powerful it is. See, we have t then, since time is in the denominator. See, when time's in the denominator, when it becomes larger, then my power then gets smaller. So that's kind of what power is. So it looks like we have a lot of concepts here, kids, but it really is not that hard, this unit. Okay, we're talking about kinetic energy. We're talking about gravitational potential energy. We're talking a little bit about thermal energy. We have this idea called work, and that's what gives objects their energy. We can do horizontal work. That can give objects kinetic energy, or we can do vertical work, which gives objects gravitational potential energy. And finally, we can talk about how quickly energy or work is done. That idea is called power. So for example, let me just give you one other detail here. Maybe your parents say, hey, can you go grab me a light bulb? And you say, well, what wattage do you want? 60 watt, 100 watt, whatever. Well, that's the same kind of idea with electrical power, electrical energy. So we might have 100 joules worth of electrical energy being consumed every second. That would be a 100 watt light bulb. Okay, we might have 60 joules over 1 second. That would be 60 watt light bulb. So this unit and this concept power comes into play with other types of energy also that you might see with some other units, maybe like electrical energy, for example. Okay, kids, that's kind of the wrap up, the general idea of this unit. We'll talk to you later. Bye.